Assalamu alaikum students. Welcome to the course CS371 Data Communication and Networks. I am Dr. Muhammad Munir Omar. Our today's topic is wired LANs, the Ethernet. We can say that in today's lecture we will be studying IEEE 802 standard, which is about Ethernet. These are the contents for our today's lecture. First, we have IEEE 802 project, then introduction to 802.3 standard, which is for wired Ethernets, then IEEE standard for LANs. Here we will compare the IEEE standard with OSI and other models. There is some differences between the other models and IEEE standard in the data link layer and physical layer. Then we have LLC, logical link control, and MAC, media access control. These two are at the data link layer. We will study about these two. Then Ethernet evolution through 4 generations, the frame structure of 802.3, the Ethernet address. These are also known as physical addresses or MAC addresses. So in these addresses, we will also look into the unicast, multicast, and broadcast addresses. And at the end, we will have a look into the categories of standard Ethernet and their implementations. The IEEE standards. In 1985, the Computer Society of the IEEE started a project called Project 802. This project was started to set the standards for intercommunication among equipment for a variety of manufacturers. Project 802 does not seek to replace any part of OSI or the Internet model. This was actually defined to specify functions of physical layer and data link layer of major LAN protocols. This standard was adopted by the ANSI, which is American National Standards Institute, in 1987. Then the International Organization for Standardization, ISO, also approved it as an international standard under the description of ISO 8802. The relationship of 802 standard to the international OSI model is shown in this figure. The IEEE has subdivided the data link layer into 2 sub layers. These are the logical link control LLC and the media access control MAC. IEEE has also created several physical layer standards for different LAN protocols. If we compare this IEEE standard with OSI or any other internet model, then we have similar layers, but these layers are divided into sub layers. The data link layer is divided into 2 major layers, that is the LLC and MMC. MAC. The MAC is further designed for different type of networks. We have Ethernet, token ring, token bus, and so on. Also, the physical layer might have of different types. These are Ethernet physical layer, token ring physical layer, and token bus physical layer. Now, let's have a proper introduction about Ethernet. So, the Ethernet is the most widely used local area network LAN technology that defines wiring and signaling standards for the physical layer of TCP/IP. Ethernet is one of the most widely used standards for computer networking and the general data communication. The networks we are using actually follow the IEEE 802 standard, that is for the Ethernet. The Ethernet was actually in the beginning, this was capable of having a support for 10 megabits per second. But today, fast Ethernet and gigabit Ethernet support data rates are 100 megabits per second and 1 gigabits per second, respectively. Also, we have a support for 10 gigabits per second available for users. An Ethernet LAN may use coaxial cables, then unshielded twisted pair, and also fiber optic cables. In the coming slides, we will study about this 10 base 2, 10 base T, 100 base T, and 1000 base T. Now let's have a look at the LLC, the logical link control in the IEEE standard for LANs. As we know that the data link control handles framing, flow control, and error control. We have already studied these things in our previous lectures. So in IEEE project 802, the flow control, error control, and part of the framing duties are collected into one sublayer called the logical link control, or the LLC. The framing is handled in both the LLC sublayer and the MAC sublayer. The LLC, the logical link control, provides one single data link control protocol for all IEEE LANs. So, in this way, the LLC is different from the media access control or MAC sublayer, which provides different protocols for different LANs. Now, if we have token ring, so for that there would be different MAC sublayer or media access sublayer, but we will have same LLC for token ring, for Ethernet, for bus, for any sort of topology. We will have same LLC but different MAC. A single LSC protocol can provide interconnectivity between different LANs because it makes the make sublayer transparent. Next, we have the MAC sublayer. IEEE Project 802 has created a sublayer called Media Access Control or MAC that defines the specific access method for each LAN. As we know that we may have different type of LANs, so for each type of LAN there would be a particular MAC sublayer. So by specifying a particular method, we can take an example like it defines CSMA CD as the media access method for Ethernet LANs and the token passing methods for token ring and token bus LANs. So for each type of LAN, there would be some different sort of mechanisms or methods. So those methods are defined by the MAC sublayer. The framing function is also handled by the MAC layer. We have already studied this thing. In contrast, the LLC sublayer, the MAC sublayer contain a number of distinct modules. Each defines the access method and the framing format specified for the corresponding LAN protocol. Remember one thing, if we have different type of LANs, for all those there would be a single LLC, means that the LLC would not be different, but the MAC sublayer would be different for different type of networks. By different networks, I mean that there might be tokening, there might be Ethernet, bus, etc. Standard Ethernet. The original Ethernet was created in 1976 at Xerox Palo Alto Research Center, Park. Since then, it has gone through 4 generations. So we are going to look into those 4 generations. Here we have standard Ethernet that has support for 10 megabits per second, then fast Ethernet having 100 Mbps, gigabit 1 Gbps, and 10 gigabit that has 10 Gbps. So the Ethernet evolved from 10 Mbps to 10 gigabits per second since 1976. The Ethernet frame contains 7 fields: preamble, SFD, destination address, source address, length or type of the protocol data unit, data and padding, and the last is CRC, cyclic redundancy check. Ethernet does not provide any mechanism for acknowledging received frames, making it what is known as an unreliable medium. Acknowledgements must be implemented at the higher layer. Usually we use transport layer for this purpose. So we can say that this layer is also unreliable. So this is the format of MAC frame. We are going to discuss all these components one by one. So the first one is preamble. It contains 7 bytes, or we can say 56 bits of alternating 0 and 1s that alerts the receiving system to the coming frame and enables it to the synchronize its input timing. This is mainly used for alert and a timing pulse. This block, these 7 bytes, allow the stations to miss some bits at the beginning of the frame. The preamble is actually added at the physical layer and is not formally part of frame. Next is SDF, start frame delimiter. This is the second field. It has 1 byte. It signals the beginning of the frame. The SDF, or the start frame delimiter, warns the station or many stations that this is the last chance for synchronization. In this 1 byte, the last 2 bits are 1 1 and alerts the receiver that the next field is the destination address. So here we have a flag for SDF. These last 2 bits identify that beyond these 2 bits or beyond this one, the destination address starts. Next is a destination address, or DA. It has 6 bytes, contains the physical address of the destination station or the stations to receive the packet. Then we have source address. So it has same 6 bytes and used for storing the address of source station. Then length or type. This field is defined as a type field or length field. The original Ethernet used this field as the type field to define the upper layer protocol using the MAC frame. The IEEE standard use it as the length field to define the number of bytes in the data field. Then we have data and padding. So data, obviously we all know about data, that the data is from the upper layer which has to be encapsulated and then transmitted. So it is a minimum of 46 size and maximum of 1500 bytes. We will discuss this in the coming slides. Last thing is CRC, the cyclic redundancy check, and we have studied about the CRC in the error correction and detection lecture, and we also studied about the different types of CRC. There were CRC 32, 64, etc. So in this Ethernet, CRC 32 is used, having 4 bytes. So what would be the minimum and maximum lengths? The minimum frame length can be 512 bits or 64 bytes. Part of this length is the header and the trailer. So here we have header, then data, and then trailer. This data came from the upper layer. Now let's calculate the minimum data size. Here we have 6 plus 6 plus 2 plus 4. So if we sum up the header and trailer sizes, then we will have 18 bytes. And the minimum size for this frame is 64 bytes. So you must know that the data size must be 64 minus 18, that would be 46 bytes. In case this data is less than 46 bytes, then some bits would be padded to make it of 46 bytes. Also note one thing, the standard defines the maximum length of frame without preamble and SFD field as 1518 bytes. The maximum length restriction has two historical reasons. First one is that memory was very expensive when Ethernet was designed. It was in 1970s, so that time definitely the memory was expensive and the storage devices and also the processing devices were not capable to process bulky data or store bulky data. So maximum length restriction helped to reduce the size of the buffer. As we know that at the receiving side buffers are used, also at the sending side buffer are used to temporarily save the data which has to be transmitted or which is received. The second reason is that the maximum length restriction prevents one station from monopolizing the shared medium, blocking other stations that have data to send. So if we don't put this restriction, then one system may have a very big number for its frames, and that station may occupy the medium forever and don't allow other stations to use that medium. Frame length, remember this thing, that minimum size is 64 bytes and maximum size is 1518 bytes. This is the example of MAC address. We can say the example of Ethernet address in hexadecimal notation. We use hexadecimal notations for the MAC addresses, and we have 6 blocks, and in each block we have 2 hex separated by colon or hyphen. The size of this address is 48 bits or 6 bytes. As we know that 2 hex can be used in a single byte, so we will have 12 hex digits. As we know that each station communicating in a network uses NIC for communication. NIC means the network interface card. So the NIC must have an address that must be unique, and that address is known as the MAC address. The NIC fits inside the station and provides the station with a 6-byte physical address known as MAC address. The next thing is unicast, multicast, or broadcast addresses. As we know that a source address is always a unicast address. The frame comes from only one station. From source, it is obvious that it would be unicast. The destination address, however, can be unicast, multicast, or broadcast. This figure shows that how to distinguish a unicast address from multicast address. Remember this thing. We have 6 bytes in the MAC address, and the first byte is taken or considered for this purpose. So if the least significant bit, this one, of the first byte in a destination address is 0, the address is unicast. Otherwise, it is multi. The least significant bit of first byte, this first byte would be from left side, defines the type of address. If the bit is 0, the address is unicast. Otherwise, it is multicast. The broadcast destination address is a special case of the multicast address in which all bits are ones. So here we have an example for this purpose. Define the type of following destination addresses. We have 3 MAC addresses or 3 physical addresses. Now let's see. To find the type of address, we need to look at the second hexadecimal digit from the list. As we know that we are going to have a look on this bit, the LSB of first byte from left side. So it is obvious that the second hex in this block will have this bit. So we need to look at the second hexadecimal digit from the left. If it is even, then the address is unicast because it would be 0. If it is odd, then the address is multicast. If all digits are F's, then the address is broadcast. There we have the following. So for first, we are considering this A. This is the first byte, and this one will have the LSB, the least significant bit on left side, right side. So this is unicast address because A in binary is 1010. So here we have 0. A is also even. It is equivalent to 10 in decimal format. Second address, this is multicast address because 7 in binary is 0 and 111. 7 is also odd, so we will have this 1 bit equal to 1. So this identifies that this is a multicast address. Then the last address, here we have F. So it is broadcast address because we have F here. So if we have F, then we will have all the 4 bits equal to 1. We will have 1111. We have another example. Show how the address, this MAC address, is sent out on line. Solution: the address is sent left to right, byte by byte. For each byte, it is sent right to left bit by bit, as shown below. Here we have first, if we take a byte, so we will consider it from, if we are taking byte, so it would be taken from the left side, and if we are taking bits inside these bytes, then that would be from right to left. If you remember, we have studied this thing in the serial communication. There we studied about the big Indian and little Indian, and we studied that time that the Ethernet uses byte big Indian and bit little Indian. So byte from the right side, and inside this byte, bits are taken from left side to right side. This IEEE standard, which is for the Ethernet, defines several physical layer implementations. Four of the most common or most popular implementations are 10 base 5, 10 base 2, 10 base T, and 10 base F. So the first one is for bus by using a thick coaxial cable. Then the second one is also for bus topology, but here the coaxial is 10. This T is used for twisted pair or unshielded twisted pair, and this is used for star topology. And the last one, F, T base F, this F stands for fiber optic, and this one is also used for star topology. Remember one thing, these Ethernet implementations use digital signals. We can say these are for baseband. So for encoding, the Manchester encoder and Manchester decoders are used. We have already studied about the Manchester and differential Manchester encoding schemes in our previous lectures. If you remember, we studied this thing in digital transmission in a lecture. So the Ethernet, the IEEE Ethernet uses this Manchester scheme for encoding, for converting the bits into digital signal. The first category of standard Ethernet is 10 base 5. This was 10 base S in the beginning, and this uses a thick coaxial cable known as thick Ethernet or thick net. The nickname derives from the size of the cable, which is roughly the size of a garden hose. If you know that the size of that pipe is usually from half inch to 1 inch, and that cable, that coaxial cable is too stiff to bend with our hands. So the 10 base S, it was actually S in the beginning, was the first Ethernet specification to use the bus topology with an external transceiver connected via a tape to a thick coaxial cable. The first of the physical standard defined in the IEEE 802 model is called 10 base S in the beginning, then 10 base FIO. Now this is known as 10 base FIO. It is also known as TechNet or Tech Ethernet. A segment of the original 10 base FIO cable can be up to 500-meter long. So note that this 10 is for 10 megabits per second, base is for baseband, and FIO is used for 500-meter long cable. The next category is 10 base 2. This is the second implementation defined by the IEEE and is known as 10 base 2. It is also known as 10net, cheapnet, cheapernet, 10 wire Ethernet, or 10 Ethernet. Actually, if we compare this category with the previous one, then the major difference is the usage of different type of coaxial cable. Here, a thick coaxial cable is used to connect different devices in a bus topology, and this category the same bus topology is used, but the type of cable is a bit different. This coaxial cable is much thinner than the previous one. Also, the cable used and 10 base 2 is more flexible than the cable of previous category. The cable can be bent to pass very close to the station. Here, the transceiver is normally part of the network interface, that is the network interface card NIC, and usually we install these NICs in these stations. Now look into the implementation of 10 base FIO and also the 10 base 2. Here, as I told you, that 10 is used for 10 megabits per second, which is its speed. Base is used for baseband. Baseband is used for digital signal. And you know that we use the Manchester encoding scheme for this digital signal conversion or encoding. And this FIO is used for the length, that is 500 meter, means that this cable can be installed for a distance of 500 meters without using any sort of repeater or digital device. So here each device is connected with a transceiver. This transceiver is actually in outer part of the station, means that it is not an installed component inside the station, and the NIC is installed inside here in the transceiver, and this transceiver is connected with the backbone cable by using a tap. The distance between the transceiver and a system can be up to 50 meter, and as I told you that the entire cable can take up to 500 meters. We can extend this 500 meters by using a repeater in this cable or network. The next implementation of 10 base 2, again 10 for 10 megabits per second. This is baseband, and this 2 is actually used for 185 meters. In this type of network, there is no external transceiver. The NIC, network interface card, is installed inside these systems, and these systems can be directly connected with the backbone by using taps. Note one thing, that the collision here occurs in the thin coaxial cable. This implementation is more cost effective than 10 base FIO because thin cables are less expensive than thick cables, and the T connected to the taps or to this backbone are also less expensive or cheaper. So the installation is much simpler because there is no external transceiver in such type of network. However, the length of each segment cannot exceed up to 185 meters, that is close to 200 meters. This 2 actually identifies 200, but it is not 200, it is up to 185 meters. If we increase this distance, let's say we install a network having a cable length up to 200 or 190, then we may have attenuation in this coaxial cable. Now we are coming back to the categories. The next two categories are 10 base T and 10 base F. 10 base T is the most popular standard defined by the IEEE 802.3, and here the T stands for twisted pair. This is also known as twisted pair Ethernet, and this type of network is commonly used by different LANs. This type of Ethernet uses a physical star topology. These stations are connected to a hub via two pairs of twisted cable. This is very common. We have seen many switches in our labs, so that is actually the implementation of 10 base T, or the advanced version of 10 base T. The next is 10 base F. This is similar to 10 base T in that each station is wired into a fiber optic hub in a star topology to form a network. So here we are using twisted pair, and in this category we are using fiber optic. The length is quite different. In the previous case, the maximum length is 100 meters, and here the length is up to 2 kilometers. This length can be extended by installing the repeaters. The 10 base if is also a common Ethernet. It uses star topology to connect stations to a hub. These stations are connected to the hub using two fiber optic cables. As we know that the fiber optic cable is unidirectional, so two fiber optic cables are used for the connectivity. Now here we have the implementation for 10 base T. So the T is used for twisted pair. We use a central hub. It can be a switch. Usually we are using switches in our labs. So the devices are connected with this switch by using two pairs of UTP cable, and at the end of cable we are using RJ45 connectors. We have already seen this thing in our labs and also discussed this thing in our several lab implementations. Next is T base F. So the F stands for fiber optic. Again, here we have a hub, and the devices are connected through fiber optic cables with this hub. The connectors used can be SC or ST. Here these slides are prepared from Data Communication and Networking, 5th edition by Behrouz Ferozan. If you have any question regarding this topic, you can put your comments in the KCMS. Thank you.